on test number 6. Okay, test number 6. Last test of the semester. This is chapter 7. 7.1 through 7.4. Remember, before the break, we did 7.1 and 7.2 as one section together with momentum and impulse. And then after the break, did somebody accidentally connect? Oh, that was probably Mr. Joseph by accident. Then we did 7.3 and 7.4 after the break these last couple days. So let's backtrack, okay? Let's backtrack to section 7.1 and 7.2. We'll start there. We had 2 formulas in that section. 2 formulas. The basic most formula was P equals mv. What was the other formula?
Delta P equals mt.
Ft. Very good. Delta P equals Ft. So let's take a look at these 2 formulas and think about where they may be used. First, P equals mv. What does that tell me? What does P equal mv tell me? Momentum. So momentum is a function of what? Mass and velocity. Good. Momentum is a function of mass and velocity. So, I have a question for you, and you should recall this question. Could a truck have less momentum than a ball?
Yeah.
What'd you say? Yeah? I hope you said yes. Why? Give me an example of when it would.
Because like the truck could have the velocity of the
Yeah. If the truck is not moving, right? The truck is at rest. What's its momentum? 0. Okay, so it's 0. If the truck's momentum is 0, even if this pen is moving very slowly, it has more momentum than the truck does. What's the second example? What if the truck is moving? What would the ball have to have?
It would have to have a lot.
A lot of velocity, right? For a moving truck to have the same momentum as a ball, the ball needs to be moving at a ridiculously large velocity. Okay? That is going back to the first beginning thing we started with 7.1, where I asked you a question. A bowling ball has a mass of this and a velocity of this. How could a bouncy ball have the same momentum? And you recognize that the velocity of the bouncy ball had to be ridiculously large compared to the velocity of the bowling ball to compensate for the lack of mass. If you got a lot of mass, you could have very little velocity and still have a lot of momentum. That's the linebacker. But if you're a running back and you have very little mass or less mass, you need to have most likely more velocity to win that battle of the collision there, right? Okay, so momentum is based on mass and velocity. P is really written for progress, not to be confused with power or anything else. Okay, P is not power, P is momentum. That's the idea of just basic momentum. Second was the momentum impulse theory, which tells us the change in an object's momentum is equal to the impulse delivered or the impulse felt by that object. So let's jot those down because I can't tell you how many people made mistakes on this in the last class. I asked the question about impulse and I got a blank look from some. Impulse is Ft. That's what impulse is. We jotted this down in 7.1 and 7.2, but a lot of people seem to have forgotten that. That's what impulse is. And this is literally change in momentum. Okay, change in momentum. So if you could find the impulse acting on an object, F times t, it's equal to the change in momentum. Usually, because, think about what Ernest told us a minute ago. Momentum is a function of mass and velocity. So I could give you a problem without any masses involved, without any velocity involved, and just give you the force and the time period. And if you could calculate impulse by doing force times time, you would, as a result, be determining the change in the object's momentum without even having mass and velocity. So if you know there was an example in your problem set that said a soccer ball is kicked with a force of 1,250 newtons for a time period of 5.95 times 10 to the negative third seconds, what is the impulse felt by that object? It's just F times t. The problem could have been written as this. Instead of saying what is the impulse, it could have said what is the momentum felt or the momentum change in the object. And whatever you get for the answer for impulse is the change in momentum. I'm not asking for the velocity. I'm not asking for the mass there. I'm just saying that if you find the impulse, you also have the change in momentum because those two things are equivalent. They're equivalent to one another. Now, if the mass and the velocity, initial and final, are kind of given, and information about force is given, then you need to rewrite this formula and break it down. Delta means change. Change means what? Very good. Okay, and as Matei noted, you don't have to show that middle step if you remember that. That's fine. I'm showing the work. We don't have to, okay? PF minus PI, but yeah, PF is final momentum, which is MVF. PI is initial momentum, which is MVI. Questions? Does that make sense? If you're given information about mass and velocity and time, it would make sense to use this equation at the bottom. What's given on your formula sheet, people? Have you looked? Did you look last night? Which one's given?
The top delta P and those two.
Yeah, that's what's given on the formula sheet. So you really need to recognize that the one at the bottom that's boxed in is just a simplification, or actually an expansion, if you will, an expanded form of delta P. That's all it is. Okay? Yeah?
Can you repeat the example of momentum? Because that's what that screws me up.
So,
You said something about like a car, like is the car moving the same momentum as a
ball?
small object? Yes.
yeah. So how do you find momentum? Mass times velocity, right?
Yeah.
A car's mass is so much greater than a ball, isn't it?
Yeah.
So if the mass of the car is really high and the mass of the ball is really low, the ball has to have a really high velocity and the car has to have a really low velocity for those momenta to be equal.
Okay.
That's all I'm saying, yeah. Or the car is at rest. And then if the ball has any velocity, it's got more momentum automatically. Okay? Other stuff to think about. Here, other stuff to think about. Remember, we give the examples of the egg toss, throwing an egg back and forth. What do? You cradle it. You have soft hands. Why again? What are you doing by using soft hands? Right, what are you doing?
We're like slowly taking the speed away from it.
Yeah, you're slowly adjusting the speed of the object. As a result, what are you physically doing to one of our variables here? The momentum is changing for sure by catching it, yeah. But more specific, by using soft hands.
Are you like decreasing the impulse?
The impulse stays the same because the impulse is equal to the change in the momentum.
Not a force.
Yeah, you're decreasing the force because what are you increasing? If this goes down, time's got to go up for this to be the same. Think about it for a second. Ready? Okay, let me explain because it's a little bit tough to see this. So, if I were to throw the egg twice, okay? I first start and throw it once, Ernest. And I throw it once, okay? That's the first time. He caught the object. I gave it a certain velocity to start. It ended with no velocity, so the change in momentum is some value. Let's say 10. So the change in momentum is 10. I do the same thing. Try to catch it I throw it to him and there's no give at all. Yeah. So he catches it here. And in that case, the change in momentum is still the same because I gave it a certain momentum to start. It stopped at the end. So the change in momentum was identical in both cases. But if you catch it like this, you're increasing time. This number is the same. This whole number here, this delta P, is 10, or whatever it is. So this is not changing at all in both scenarios. This is not changing. What's changing is this over here, the time and the force. By catching it with soft hands, you increase time. Increasing time decreases the force there. Does that make sense? Okay, the force has to go down for P or delta P to be a constant. Put a number here, put a number in for time to get a force, and then change the time. By increasing the time, the force has to go down to yield the same product. Okay, this is like your direct and indirect variation, right? F and T are indirectly related. You have more time of contact when you catch it, lower force. Your car hits a tree, the airbags deploy. Why do they deploy? Increase the time. If you hit your dashboard like this, versus hitting your dashboard by hitting the airbag, slowing down, and then connecting with the dashboard, all of that time occurred to slow you down. Therefore, the force you felt would decrease because the time period went up. Okay? Does that make sense? Does that make sense? Yes? Time and force are indirectly related there. Yeah?
If there's a problem that gives you like the mass, the velocity, and the force, so you have to find the time, but also, like, what would your formula be for that?
So I would use this one here, but you're probably given something about starting from rest or coming to rest at the end. So this is the formula because, ready? If you're given the initial velocity of like 10 meters per second, you're given the mass, you're told it comes to rest at the end, that's 0. You're given the force, you can find time. Or you're given time, you can find the force. So any of these variables could be the unknown. But this is the formula you're going to use for a scenario like that.
And there's no way to find the change in momentum without
Without actually actually having either, if you have the force and the time, you get the impulse, which is the change in momentum, or you need to be given the mass and the velocities to get the change. Either way, you're given one side of the equation or the other, will give you the change in momentum. Hey, write yourself a note. This is great that Nick pointed this out. And you can thank Nick, by the way, for changing that assignment. I made 104 instead of 106. He pointed out a problem with it, so that's why we did that yesterday. This here is only involving one object. Sure, maybe it's a baseball bat hitting a ball, but the ball is the object at hand. When there's a collision and the two objects move afterward together or separately, we jump into 7.3 and 7.4. Right? When I'm giving you two masses and all that kind of stuff, you jump right into 7.3 and 7.4. But if you're only given one mass, and you're not like trying to find the other mass, you're going to use this equation right here. Okay? Yes?
We go over a problem.
Yeah. What do you got?
68, 7-1, I have a picture.
Oh, perfect. You want to just read it out loud?
Yeah.
Go ahead.
Soccer player 1 has a mass of 45 kg and moves to the right with a speed of 1.4 meters per second. Soccer player 2 has a mass of 32 kg and moves to the left with a speed of 2.1 meters per second. What are the direction and the magnitude of the total momentum of the two players?
Okay, so this is a problem that makes you think right off the bat, I need to use 7.3 and 7.4 because there's two objects, right? There's nothing about a collision though, is there? There's nothing about like before and after the collision. So what this is asking you is just calculate the left-hand side of 7.3's equation. Think back to 7.3, the equation. It was m1 v1i plus m2 v2i. It's right here. Take a look here. Okay, this equation, remember this? The momentum before equals the momentum after. What are we interested in though? In this problem, since there's no afterward, we're interested in the total momentum before. So all you would do is plug in those four values right here. This would be 45, would go in here. 1.4 would be here. That's a positive momentum from soccer player 1. Soccer player 2 would have a negative momentum. That goes in right here. You sum those together, and you get the overall momentum. Okay? It's a good question, guys, because we didn't really do something like that. We didn't do something where it was just like, what's the momentum in general of the system? We've done stuff where find the missing velocity, find the missing mass, find the missing whatever. But the overall momentum of a system like this, mv for the one object, mv for the second object, add them together. Gives you the overall momentum. 1, 2.
So for here, though, it wouldn't be just whatever the sums are together, because that's negative. So it would
You just add a negative number. It's
yeah,
still a
I-
sum.
I'm just- yeah.
Still a sum. Remember, subtraction is defined as a sum of the opposite. It's adding the opposite. So yeah, you could technically think of like this number minus that number if you want. Sure, it's fine. But I would think about it as a sum, yeah.
So, but for the, let's say the math section,
Mhm.
it's going to be like, so one question.
It's going to be definitely momentum impulse using the formula that's boxed in for sure. And it's definitely going to be probably two problems using 7.3 and 7.4. One elastic and one inelastic. You could expect 3 at least.
And what about the short answer?
So short answers, you know those conceptuals that you had on the problem set? That kind of stuff. The one with the person in space, like the person in space, how does he move backward if he's tethered to a rope and the rope breaks? What does he have to do?
So if it's throw whatever he has in his hands, it counter a opposite reaction.
Yeah, you could use Newton's third law to explain it, or conservation of momentum. If I want to move backward and I'm in space where I'm undergoing no forces and I throw an object that way, I'm going to move that way. Because think about it. Before I throw the object, let me give you this scenario. Okay, I'm stuck in space, and this actually, if you've seen the movie Gravity, this happens in the movie. It actually does happen. She doesn't, or he or she, I forget if it's he or she, doesn't actually throw anything. They use like the oxygen tank, and they release some oxygen. When the oxygen fires that way, it's like a rocket. If the rocket thrust fires that way, the rocket goes that way. Ever see a rocket take off? Which way does the thrust force push? It pushes down. Right? All that fire comes out the bottom of the rocket, propelling it upward. So if I'm in space and I'm standing here like this, what's my momentum? 0. Suddenly, I give the ball positive momentum. How could the system still have 0 momentum? Because momentum's conserved. I must have what kind of momentum? Negative. If it starts with no momentum in the system, and I give the object positive momentum by throwing it, I must have to have negative momentum. This is exactly the same as two ice skaters standing still in the center, pushing off. When they push off, which way do they go? Opposite directions. Hey, a little fun fact. This is something from the problem set in the other class I asked about. Think about things with directionals in this chapter a lot. Negative, positive makes such a big difference. If I were thinking about two ice skaters pushing off, and in the book there were a few examples where they gave you the speed. They told you the speed of one ice skater was 4 and the speed of the other was 2. What did you have to do to the 2 though? You got to make it negative because it's moving the other direction, right? When they push off each other. Or how about this one? How about this one? Catch. I toss this to Gabe, he catches it. If I throw it with positive velocity, the only way he can slow it down is by giving it what kind of a force? Negative force. If he throws it to me with negative velocity and I catch it, I have to push back with a positive force. You see the difference there? So in these problems with momentum impulse theory, the sign for F really does matter. The sign for F matters. If you solve and you get T and T equals a negative number, you probably forgot to make F negative or vice versa. See what I'm saying there? If you get an answer where time is negative, can time be negative? So you probably forgot to make the force negative because the force is a resistive force. It's resisting some positive initial velocity.
For momentum, for the unit, we always write
KGM over S. It's annoying.
kg
Times M. You can put KGM in the numerator and put S in the denominator. Same thing. Right? Multiplying fractions, you multiply the tops. So either way. Yeah.
Sorry, so for that concept, we could use either Newton's law or conservation.
Yeah, I mean, I would probably say using conservation momentum explained, so then you need to use conservation. You know what I mean? Let's pause for a quick second. We're going to jump to 7.3 and 7.4 examples and talk about that. But while we're doing that, Anthony is going to go through a quick demo with you. Okay, so what he and Caroline did the other day is they took 2 of these little carts, these little collision carts here. They set up one of these tracks in this track system. He's going to show you a video. You can airplane. He's going to show you a video in a minute. And what they did was they took these carts and slid them toward each other with different masses. And see the spring in the middle? They had the springs hit also, so that the spring actually compressed and then it separated afterward. And they actually took out all the data. So remember I was talking about how the lab you did was a simulation? This is actually how you take down data for a real experiment with this topic. You would have 2 objects colliding, you have the masses measured, you need the velocities before and after the collisions. It should ask you for a code when you're airplane. Is it not working?
No, I was just going to the Rainier app. So.
Okay. No problem. So he's going to show you real quick just a video of it first. All right, and then what he's going to do is we're going to go through some of the math and we'll talk about whether it was elastic or inelastic.
So for this example, what we have is it's kind of hard to tell from the video, but yeah, sorry.
Sorry, Major. You're in there.
But the cart on the right actually has 5 100-gram masses stacked onto it, so it weighs 1.01 kilograms, while the cart on the left weighs only 0.51 kilograms. And for the first one, we did just a head-on elastic collision, and you'll see the points follow as it goes along.
So what he did was he had to track these points along the way, which enables the computer or the thing to calculate the velocity. That's what he's saying.
So for this car, you can see that the car on the left, it goes, after getting hit with the car with a much higher mass, goes back faster. And there's also the points for the other one. This was for, this was the same video, except this time I did the points for the cart on the right. And you'll see this one has much less, the points have much less of a distance because that one goes back a lot slower.
More mass, less mass. Makes sense that the less mass got launched off, right? Like remember the blob, that video with energy? The little guy got shot off, same idea.
So then after that, I took the data and I used the Vernier graphical app. And this is the chart. On the bottom, that's the x velocity, and that is for the cart on the right. Yes, but this is for the cart with more mass on the right.
Yeah, because it's negative velocity.
Yeah, and up top is the displacement overall.
And when did it collide? Here's when it collided, guys, right here. Ready? Negative velocity, negative velocity, negative velocity. It collides, slows down, stops. And then which way does it go? To the right. Positive velocity, positive. Notice it was moving initially with more velocity than it moved with afterward.
And then for the other cart, this is the graph for the other card. So it started much faster and then had negative.
So it was moving to the right, the other one came in, they collided, and then it launched off to the left with more velocity. And then what Anthony did was he used a feature here that enabled him to find the average of the velocity because it was fluctuating when it took down the data points. Okay, it's a calculus app. It's using calc, the average value function actually.
So then after that, I did the calculations to see if there was conservation of momentum and conservation of kinetic energy. So here's all the values, mass 1, mass 2, velocities before and after. So when I did the calculations for momentum, they ended up actually pretty close with negative 0.16809 and negative 0.16332. Though I mean, there are a few reasons why they're not like if they would be exact if it was a perfect collision. But there was probably some loss in speed due to the springs. I probably didn't launch them exactly right, and also.
How are you taking the velocity down?
Yeah, the points aren't always 100% accurate, but it's pretty close. So
it's very close.
Okay, yeah, and then for the kinetic energy, I did 1/2 mv squared, initial and final squared there.
And that's squared. But take a look. Two objects were moving before the collision, right? So here's the kinetic energy before the collision, and he said, does it equal the kinetic energy after? Does it? No. Why not? Why do you guys think it didn't equal kinetic energy? No, mass doesn't affect it. Friction could be possible. Good. What else? Friction. The springs, when they collided, what did the springs do? Yeah, they compressed. What kind of energy goes into springs? Elastic energy, right? So some of that energy that was lost here, and if you want to find the energy loss, you take 0.121 final minus 1.096 initial, and what kind of an answer would you get? What kind of an answer? Small number minus a big number. A negative number, which means you lost energy. What kind of a collision would this be then? Even though they didn't stick together, if there's a loss in energy, what kind of a collision is it actually? This is weird because we've been talking about it kind of backwards, right? Remember, we've been assuming everything doesn't have all this loss. When two things collide and separate, we always say elastic, right?
Yeah.
We've been saying that all along. When they stick together, we say inelastic. This is in between. Remember I kept saying to you in real life, collisions, even when they're elastic and they separate afterward, there's still some loss in energy. So this is in between elastic and inelastic. Remember on the slider on the lab, it was set up to be elastic and then you moved it all the way down to 0 for inelastic? If you had put in between, this is what happens. They collide, they separate, there's some energy loss due to something, therefore it's in between elastic and inelastic. And almost all examples in real life are in between. They're not actually one or the other. Okay, it's very rare. It's more frequently occurring that inelastic occurs because sometimes when two things collide, they do stick together. And that's inelastic, for sure. Whereas elastic, it's hard for that to happen unless you're in space or unless you're in a vacuum where there's like no frictional losses or anything at all. Okay? Do you understand what he was talking about here? Do you understand how you verified this? How these numbers are similar? Some of you did this in your lab when you were doing it. You plugged in numbers and got the same answer and said check. And that was okay, that's fine. You could also have checked by solving for one of those and seeing if it was the same as your table value.
With this change in momentum, did he solve for both objects right there?
So what, you want to explain what you did here?
Yeah, sure. Well, I had all the information for both objects, so I just plugged in all the information. I have mass 1, I have mass 2, and I have the velocity initial, velocity final. So then I did all of the math for both sides and saw how close they were.
Yeah, so those are both objects. Even though you only see one number, the sum of these two added up to this number. What if the first object hadn't been moving? How would this change? To start, if the first object wasn't moving.
Well, wouldn't it just be like half of it, this M2 and V2I?
So what would happen to this? This becomes? 0. Okay, if the first object wasn't moving. And that happened, I think Caroline in the other class did that. So if you want to look at the other recording, we did an example that was a little bit different for hers, where one was moving, the other wasn't. You had a question there before that, right?
I was just about to ask that.
Great question. And then same thing with energies, please, okay? If one object wasn't moving beforehand, the energy drops off also. Hey, if they stick together, it's the only time it gets a little trickier, and we have to do m1 plus m2 times Vf.
Is it VF squared or just VF?
For the kinetic energy, for this,
For kinetic.
it's Vf squared. Then it would be 1/2 m1 plus m2 Vf squared for kinetic energy. For momentum, it's just m1 plus m2 times Vf. Okay? Awesome. Thank you. Anybody else? Problem sets? Last chance if you forgot to hand them in? Okay. Send me a list of anyone didn't turn in. Okay? All right. Let's go those equations now. We're going to talk about them for a while. So let's write them both down. So we've got the elastic one you see on the board already. M1. These are on your formula sheet. V1I plus M2 V2I equals M1 V1F plus M2 V2F. That's for elastic collisions. And the delta KE for this is 0. Okay, that's our scenario for elastic collisions. They hit, they separate, there's no loss in energy. So if you were to calculate KEF and KEI, these numbers would be absolutely identical for an elastic collision. Okay, for an elastic collision. For an inelastic collision, we've got, we've got a lumped mass at the end because they stick together. In this case, delta KE is some negative number. Why is it some negative number? Because the system loses energy. It's always going to be a negative number there. Okay? It's always going to be a negative number here because the system loses energy. Inelastic could also vary a little bit. Instead of the objects combining afterward, they could also start together. Remember the truck, the pickup truck with the steel beam in the back? The pickup truck was driving, and then the steel beam falls out the back of the truck. Those objects started together, didn't they? And then suddenly what happened? They separated. Or imagine, I think of a good example of this. Perfect. Quarterback in football. A quarterback in football is usually not throwing from the set. He's not usually saying, okay, I'm going to do this. A lot of time quarterbacks are moving when they throw. So imagine a quarterback that has good mobility like Aaron Rodgers. He's always running. He's always moving. And he's throwing while he's moving too. I'm thinking about like a good passing quarterback also that can run well. So he's running, right? He's always running. He's always throwing at the same time. If he and the ball are moving together first, right? If they're moving together, the ball is M1. He is M2. They're running together. And then he throws it as he's running maybe. The ball separates as M1, he's M2. So in that case, it's still inelastic, but it would be this. Let's just jot this down because this is a little bit different, but this could happen also. This would be the scenario. The quarterback and the football, they're moving together first with a given velocity, right? He's moving, he's trying to find an empty spot or an empty spot in the pocket to throw, and then he launches the ball, so they separate now. It's the opposite, exactly. This is a collision that sticks together. This is an explosion, if you think about it. What's an explosion? An explosion, exactly, it's a separation, exactly. Anybody that I talked about this with Halo, right? I talked about frag grenades, I think I mentioned here. When you throw a frag grenade in a video game, you're throwing it with some velocity. So the grenade acts as one object with a velocity, and then what happens to it? It explodes into a million pieces of little shards, shrapnel, and those are all little separate pieces afterward. Okay, so that last thing in blue there is an explosion you could think of. What else? And that would also involve a change in kinetic energy because it's inelastic. For kinetic energy in the test, you could definitely expect me to ask questions such as, determine the loss in kinetic energy as part B after you've found maybe the missing velocity. Or I might say, here's the scenario. I give you a bunch of stuff with velocity, and I say, is this collision inelastic or elastic? And maybe you just have to find delta KE. If it's elastic, what would delta KE be? Zero. At the top, right there. But if you get a negative answer for delta KE, it's inelastic. Okay, or a number, rather. Some number for delta KE.
And in those objects, you would know how, you would have to get like how many objects are moving, how many are not, so that we know.
You can probably tell by the context of that also, but I might not tell you if they stick together or not on purpose, so that you don't know whether it's elastic or inelastic. Okay? I might say they happen to have the same velocity afterward. Doesn't mean they stuck together though, actually. They could actually both be moving at the same velocity afterward, but they could be separated, right? If I give you two different velocities afterward, you could almost already assume it's elastic, right? Because they're separate afterward. Hey, multiple choice. I am probably going to also give you some like simple math in the multiple choice. For example, if you double velocity, what happens to momentum? What is it? It doubles. If you triple the mass, what happens to momentum? Triples. Because mass and velocity are directly related to the momentum of a system or an object. Mass and velocity are both directly related. Last chapter, we had to worry about squaring the velocity. Remember that? Because it was 1/2 mv squared. So if the velocity tripled, last chapter, if the velocity tripled, the kinetic energy went up by a factor of 9. You had to square it. You don't have to worry about that anymore. What if this? How about this? What if the mass triples and the velocity doubles? What does the momentum go up by? 6. Think about it. Okay? If the mass, so this is, I'm going back to like multiple choice now at this point. If the mass doubles and the velocity triples, what do you end up with? You end up with 6 times what you started with. See that? If you started with just mv, and then suddenly you double, that's a 2, not a 12. And then you double the mass and triple the velocity, 2 times 3 is simply 6. M times v is mv. So you're getting 6 times what mv was. 6 times more. It goes up by a factor of 6. Yeah, Ernest.
When you're looking for like the loss in kinetic energy, you use the first part.
Final minus initial.
Okay.
Yep. Any problem that asks you to find the change in something, final minus initial. Okay? I'm saying that specifically because with momentum, it's also the case here. Change in momentum, delta P, is final momentum minus initial momentum. Okay, it's always final minus initial. That's why the answer here would be negative. Final momentum, look at it, it's tiny. Final energy is small. Initial energy is much larger. This would be a change that is negative in the case. All right? Other questions you have? Problem set questions, lab questions, homework questions. I told the other class I'm going to push 7-4 back to do Sunday. So just at least get the lab done tonight. I recommend doing 7-4 if you can find the time for it. I know you have a math test, and I know you also have homework for math, all right? Always due tomorrow. So I get it. So I'm going to make the due date for 7-4 Sunday instead. But if you have the time to do it, try to do 7-4 tonight also. It's just good practice. But the lab is just as good as 7-4. So if you're going to do something, I'd rather have the lab done by tomorrow, and I'll push 7-4 to Sunday. Okay? Yeah.
So for inelastic, the change in kinetic energy is negative?
Yes, because it's going to lose kinetic energy. What was the second part? What?
Oh, okay.
You sure?
Yeah.
Okay. But for elastic, what's the change in kinetic energy?
0.
0. Because elastic collisions conserve kinetic energy. Energy is conserved for an elastic collision. Momentum is always conserved, right? Momentum is always conserved, whether it's elastic or inelastic. It's kinetic energy that may not be. Kinetic energy is conserved for elastic, but kinetic energy is not conserved for inelastic. That was one of your problem set questions also. Nick.
In the problem sets, last night for 1 to 5, you talk about the kinetic energy, how it's final minus initial.
Final minus initial, yep.
It said to find how much does the kinetic energy of the system decrease during the
So-
what decreases it initial?
So technically speaking, yeah, the answer you want to give there would be a positive answer because it says how much does it decrease by. Yep. So you should, I would still, it doesn't matter, but I would still write it as KF minus KEI. You get an answer, the answer is negative. So say the answer is negative 25 joules. Your answer would be 25 joules. See what I'm saying? Because the problem said, how much does it decrease by? It decreases by 25 joules. Or you could say, the energy change is negative 25. That's the same exact statement. Okay? That's a good question. What else? West means negative, east means positive, left means negative, right means positive. We need our directionals in this chapter for sure.
We only use that in our answer for force and when it asks for which direction it's moving, right?
Mm-hmm.
Alright. So
Okay,
not
velocity and force.
And velocity.
The velocity is the direction it's moving. If it's moving to the right with 5 meters per second, that's positive 5, right? Left, negative 5. Remember, force and velocity are vectors. Remember that term we keep using? A vector has a number and a direction. Always. This is like a midterm review question right there. And that's like one of your midterm questions. What is it like? If I give you a multiple choice about vectors, right? Velocity and forces are your best examples for vectors because they not only involve a value but a direction. If I said to you the speed is 7 this way and the speed is 5 this way, you don't need the positive or negative because speed is just whatever the number is. But the velocity would be positive 5 and negative 7. I'm trying to think of other stuff. This is what happened in the other class. We had about 3 or 4 minutes left at the end. We have about 5 still at least here. Other questions you have? Yeah? Yeah. No other problem set questions? Everything else you were pretty confident in? Feel free to look and ask questions on it. That's why I always push you guys to get it done on time so we can sit here and discuss. Jake, and then Gabe, and then Nick.
Can we go over problem 105?
105? You want to just read it to me slowly? Go ahead. Yep.
A 25,000 kilogram train car moving at 2.5 meters per second collides with and connects to a train car of equal mass moving in the same direction at 1 meter per second.
At what?
At 1 meter per second.
Okay.
And I just got cut off.
What do we have after that? Go ahead.
Going for the equation M1, V1.
Well, let's wait to see what happens. We haven't had we need to read the end of the problem to know whether or not it's going to be this or if they're going to stick together. I don't think he...
I said, what is the speed of the connected cars?
Connected.
Yeah.
Key word there, connected. What kind of a collision then, right away? Connected. Inelastic. So, Rye, go ahead.
M1, V1 plus M2, V2 equals 20 of M1 and M2 VF.
Now, if we look at this, are we given all the information we need? Sure, we are. We have all the masses. We've got the initial velocities of the system. We have the initial velocity of the system. We could find the final velocity, VF, right here. Again, we know this, we know this, we know this, we know all of this stuff. We know these both, right? But we don't know VF. All you got to do is plug in here and solve for VF. Do you want to go over that or you want to go over the part B? I think there was 2 parts to this problem, right? Were there 2 parts of the problem or is that it? What did you get for VF, Jake, when you did it? Did you get a number for me? Anybody got a number for VF?
1.75.
And the reason he got that, it was a positive? It should be, right? Why should the answer be positive? Why should the answer be positive, right?
Because you can't, not moving at negative velocity.
Yeah, both train cars right here. In your mind, you need to picture this. Train car 2.5, train car 1, velocity. Here's what's happening. Here's what's happening. Suddenly, they connect and then they move together. So they were both moving positively, the other one caught up, they connected, and they're still moving positively. So this number should have been positive. It's between 2.5 and 1 because they were both moving to start, so it can't be less than the velocities of them separately. It's not going to be less than them, but it's going to be between those. Just like earlier, if you remember earlier yesterday, when one car was at rest and the other was moving, say this was moving with like 20 meters per second, they collided, and then they moved with something less than 20. But it was really between 0 and 20. So your answer should be between the velocities you started with. You see how the answer makes sense here? You need to be able to answer those kinds of questions. I will give you problems that ask you about the sensible nature of the problem. Now, I might also, I'll finish this in a second. I might also ask you questions in multiple choice and short answer where I give you the whole scenario. It's not about calculating numbers. It's about explaining the actual answer. Is that clear? So, for example, 2 objects collide with different masses and they separate afterward. Why does the one that's heavier move slower? Right? So think about, remember the ice skaters? Ice skaters start together in the middle of a ring. Heavy ice skater, lighter ice skater. The 2 things push off of each other. What's going to happen naturally? The heavier object isn't going to move very far. The lighter object will move much easier because of the conservation of momentum there. Okay, the momentum of the system to start is 0. So if the bigger object starts moving this way, it can't move with much velocity because it has more mass, less velocity. This one, less mass, more velocity. So they move like that instead. Okay, that's the kind of sensible question you could have. Part B of this, as Nick mentioned earlier, said find the decrease in the kinetic energy in the system. So before the collision occurs, we've got kinetic energy from both objects. The first one has a mass of 25,000 and a velocity of 2.5. That's the kinetic energy for the first object before the collision, right there. What's the kinetic energy of the second? Well, it's the same thing, just different values. The masses happen to be the same. The velocity is now 1. And then after they collide, what's the mass after they collide?
25,000 times 2 is
Okay?
1.75.
Good. Times the final velocity you just solved for in the first part, squared. So this is the mass of the combined system. This is the velocity after they collide. Square that number. Was there a difference in these numbers? Was there a difference in them?
Yeah.
Because it was an inelastic collision. What, did you get a number for this?
14,062.5 joules.
1462, like that? So I got to move my comma?
No, it's 14,062.
Oh, 062. Got it. 14,062. Joules is the change in kinetic energy. Now remember, this number is negative because the final kinetic energy was smaller than the initial. So it is negative because the problem said find the decrease in energy. You could have just said the decrease is 14,062. Or you could make the statement that the change in energy is negative 14,062. Both ways are acceptable.
So you do
Okay.
final minus initial.
Final minus initial. Always. You keep asking me that. It's like the 4th day you've asked me that now. Yeah, that's all right. No, but final minus initial. Let that get in your head.
So KEI is all the initials. Like I'm confused with the 50,000.
What after they collide? Is it 2 masses or 1?
2.
But aren't they stuck together?
No.
They were, yeah. In this problem, they were. Sorry. So I didn't mean to set you up like that. So the 2 cars are moving, right? And then suddenly they join together. They lock together. So now they're moving as 1 mass. And since their masses were the same, the 1 mass is now 50,000. And what was the velocity they were moving at? Your answer of the overall velocity of the system after the collision, right there. So these are the 2 objects separately before the collision. This is, since they're together after, is only 1 object. If they hit and separate, you'd have, afterward, separate kinetic energies. Here, it was together. Okay?
And then when you do that, after you get the negative 40.
This comes from final, this answer, minus the answer you get from the initial. Yep. Yeah. Office hours till 3:45 today. You got 45 minutes, please. I only saw 2 people yesterday for questions. Okay? Also roller coasters. Keep that in mind. Class.